Welcome to our Consulting Specifying Engineer video discussion. I'm Amara Razgis, your host today, and I'm speaking with Rich Scroggins from Cummins. Hey Rich, how are you?
Great. How are you?
Excellent, excellent, and thank you so much for joining me. Before we get to the technical side of things, let me provide some background about Rich. Rich Scroggins is a technical advisor on the data center market team at Cummins. Rich has been with Cummins for 30 years in a variety of engineering and technical marketing roles in the power generation business. Rich has been a member of IEEE 1547 Working Group and is an alternate member of the NEC and NFPA 110 code panels. And today, we're going to talk about a lot of things, but particularly the data center industry is entering an era defined by complexity. The explosive growth of artificial intelligence workloads is creating an unprecedented power density and uptime requirement in these data centers. At the same time, grid limitations, carbon reduction mandates, and regulatory expectations are redefining how we approach backup and on-site power systems. Rich, let's start with the obvious. AI is reshaping data center design. What are the key takeaways, the surge in computing power? What is it impacting? How are we thinking about backup and on-site power systems?
Yeah, thank you. So first and foremost, the biggest concern is just the amount of raw power that data centers are requiring. Utilities are becoming strained, and there's a concern that the power requirement of data centers, utilities won't be able to keep up, and some of them are starting to mandate demand response, participation in demand response for their customers that have these large loads. And as we look at this, what we see is that utilities they have a peak power problem, not necessarily an average power problem. So what they are needing to do is have some of their large loads like data centers agree to disconnect from the grid for some period of time, and they call it a flexible load. So a load that can come on or off of the grid, and that alleviates a lot of the challenges that utilities are projected to have. So the biggest trend or most important trend that we're seeing is that utilities are mandating that data centers use their on-site power to be an asset to the grid, to remove that load on the grid. So that's the biggest and probably most important change that we're seeing. A second is the power density of the racks. The typical rack today is 30 to 40 kilowatts, per rack, and with some of these AI training loads, they're talking hundreds of kilowatts, and sometimes some are even saying up to a megawatt in an individual rack. So that is going to change how power is distributed within the server rooms, within the data halls. You're putting a lot more power into a smaller space. And so how will that change? And I think we expect to see a lot more distribution at medium voltage, because you have so much, so that limits the footprint of the electrical distribution equipment. It also limits the cost. As you're at medium voltage, you have lower current, and current drives cabling cost. So I think we see a lot more medium voltage distribution, which in the generator world can translate to using more medium voltage generator sets. The other area that we see in terms of AI loads is the volatility of the AI loads. So data center loads, the load profile is quite steady today. We have all these individual servers, thousands of servers, and each one is fluctuating between high power draw and low, but they're not synced, so they cancel each other out. So what the generator or the utility feed sees is a very flat load profile. With AI loads, that's the individual servers are synced. So when they're all peaking or dropping at the same time. So this volatility it's causing problems for other customers on the grid connection. We see flicker because of that. And also it can cause problems for the generator sets. The generator sets don't do well with load fluctuating like that. So this is energy storage is likely to be part of the solution for that, but it's a question that data center operators are still wrestling with. So three real areas where power is going to change. One is just the sheer amount of power taxing grids. A second is the power density within the data halls, a whole lot of power in a smaller space. And the third is the volatility of the loads.
Okay. And Rich, you just kind of touched on this, but grid availability has become a major constraint in many regions.
Mhm.
Can you walk us through the different use cases you're seeing? How is Cummins tackling or tailoring power strategies for each of these?
Yeah. So I would talk about two use cases. The first being what's becoming known as a flexibility use case. So meaning your data center becomes what's known as a flexible load. It can go off the grid, so it can support the utility when that's needed. And so what we what we are expecting there, and there have been lots of studies of this. Probably the most prominently cited one right now comes from Duke University. But what they're showing is that the utilities are able to absorb a lot more load without adding infrastructure as long as that load is flexible. So as long as you can take off that uh, take that load off the grid during times of peak power. And what they're looking at is it's no more than 300 or 400 hours per year and no more than 2 to 4 hours per event. So this type of flexibility really enables the utilities to take on a lot more load. They're calling this curtailment enabled headroom. So they actually do have more headroom if you're able to take those take loads offline to alleviate those peaks. So we think of that as being the flexibility use case. So being able to use your on-site assets to take the data center off grid for a period of a couple 100 hours per year. So that I think is going to be a most common use case going forward. And a second use case that I'll mention is temporary power. So we're seeing instances where data centers want to deploy at a site before the utility infrastructure is there to keep up. So it's usually going to be the transmission. It's not so much generation. But we see instances where they're looking for on-site power to temporarily, and by temporarily, I mean months to up to 2 years. Probably not viable if you have to go longer than that. Um, to run 24/7 for at least part of the facility, if not all of it, until the utility distribution infrastructure is built out. So what we see that as being, we're calling that as a kind of a bridging power use case where you're going to have some asset that's going to run continuously and then migrate when the utility is built out, the distribution is built out to more of a flexibility use case where it would be used as backup power and also demand response.
Okay. Okay. So, from a tech standpoint, what are the technical trade-offs between things like diesel, natural gas, battery energy storage? I mean, we're looking here at performance, scalability, and emissions across all these use cases.
Yeah, and so as we talked about those use cases, it, those are the three that I think are really either in play now or on the cusp of a widespread adoption. So I'll start with starting with diesel. Um, diesel is kind of the incumbent in backup power. It's worked well for a long time. The challenge comes if you're using it for something other than emergency power, for non-emergency, and the EPA's definition of emergency is only when the utility is out. So if you're doing a demand response, if you're doing flexibility, then it has to be what's known as a Tier 4 certified product. And that becomes a bit of a challenge. I'll just talk a little bit about Tier 4. Uh, so Tier 4 emissions levels, there it's about a 90% reduction in NOx and oxides of nitrogen, um, below what a common Tier 2 level, which is the de facto standard for generators of this size. The common, it's table stakes for standby generators. So the Tier 4 levels, it's about a 90% reduction, and that can be achieved with a third party after treatment system from any number of suppliers. A challenge though is if it needs to be a certified product, which is a requirement from the EPA for non-emergency operation. It has to be something certified by the manufacturer, and also has to have what's known as an inducement, meaning the generator will shut down if the emissions controls stop working. And that's been a kind of a poison pill for the data center space, because having to shut down means that becomes kind of a single point of failure for the generator set. So we see that changing though, because the demand response, whereas it was something that was optional in the past, if it's becoming mandatory now, it's becoming mandatory. Um, and if it's no longer an option, that forces operators to take that Tier 4 certified product. Now there has been a recent development, recent interpretation by the EPA, where they will allow an emergency generator set to be deployed in a non-emergency operation if it's mandated by the utility for up to 50 hours without having that Tier 4 certification. So that's something that will play well into this flexibility use case. Um, it gives them 50 hours where they don't have to have a Tier 4 certified product. Now, there are still challenges, though, even with that, because some of these sites, they are so large, and they are maybe located in what's known as an emissions non-attainment area, an area where the air quality is already somewhat poor. They will have maximum operating hours to keep the cumulative NOx from the site for the year under what's known as a major source threshold. So in these locations, and this is under Title V of the EPA, a site is limited to some amount of NOx emitted by the entire site for the entire year. So it's not a problem in a small facility where you have two or three generator sets, but in some of these large data centers where you have 80 megawatts or 100 megawatts, and you have diesel backup for all of those, um, it isn't going to be too many hours before you could potentially exceed those major source thresholds. So that's something that becomes a challenge too. Run hours can be limited by those major source thresholds. So that's the big challenge with diesel. Um, a second technology it's available today and is getting much more of a look in the data center space is natural gas generator sets. Um, they certainly have the advantage in that they are lower NOx than a diesel generator set. Um, just kind of the rough rule of thumb is that a natural gas generator set has the same NOx emissions as a diesel with that Tier 4 after treatment. So it's a lot better there. Um, and also um, in terms of these flexibility use cases where they're running hundreds of hours per year, uh, the operating expense becomes better for natural gas. The fuel costs are lower. Um, if you look at total cost of ownership between diesel and natural gas for a standby operation where you're running only say 50 hours a year, diesel's going to be better in terms of total cost of ownership. But the longer you run, the more operating hours you have, the better natural gas looks like uh, for total cost of ownership. So there's a couple of challenges with natural gas, though. One is simply natural gas pipelines. Um, they aren't always available in sufficient capacity for some of these large data centers. The big data centers aren't usually in the urban core. They're out in a little bit more of a rural area, and while there will be natural gas pipelines out there, not necessarily, there won't be necessarily in sufficient capacity to run a 100 megawatt facility on natural gas. So that's a challenge. It's natural gas won't be a solution everywhere. I mean, because extending these pipelines, I've heard estimates of over $2 million per mile to extend the pipelines, and then there's all the permitting and all that stuff that goes with it. The other challenge with natural gas generator sets is the transient performance. They don't start up and take load as fast as diesel does, and in the event of loads coming on and off lines, they don't respond as quick. Um, so some of that can be alleviated with natural gas. For example, for server loads, they're usually backed up. They're almost always going to be backed up on a UPS. So you can extend that UPS runtime to better enable your natural gas generator set. Um, that has limitations in how much that can be done. I mean, it does impact the life of the batteries, the UPS batteries, and there um, could also be some service level agreements uh, that prevent you from running too long of a period on natural gas. And the other consideration with natural gas in terms of the startup time is there are also cooling loads that aren't typically supported by UPS, and those cooling loads, that can't go too long without power before you start having a kind of a thermal runaway event, right? So if you have a utility outage, you have your servers on UPS, they're still operating because they have the battery power, and so they're still generating heat and need to be cooled. Whereas if your cooling loads have lost power, um, you know, you can run into a thermal runaway. On the order of 30 seconds is kind of the amount of time. So there are fast start generator sets, gas generator sets that come online, but you do potentially have that race condition. And the third technology that we've talked about for this flexibility use case would be battery energy storage. Kind of a newer technology in this application, but there's a lot of interest in it in this space. The challenge there is autonomy. Um, how long can they go? The typical data center is going to have 24 or 48 hours worth of fuel stored on site. That's the expectation is that we can keep running in a utility outage for 24 hours. That's not really practical with battery energy storage technologies. Um, what seems, the most common technology being lithium ion, what seems to be the point of viability is about 4 hours. So beyond about 4 hours, that's not a viable source. So, um, if you were to use only a battery energy storage system as your backup, it would you would certainly need to change your operating modes. Certainly not going to be an option for all data centers, but they can certainly complement other assets there. So I would say those are the main challenges with the more common assets that we'll see in data centers to address this power explosion and constrained grids.
Okay. Let me shift gears just slightly here, Rich.
Okay.
More data centers are considering demand response or grid interactive operations. What does that really mean for generator sizing or maybe control topologies or integration with utility standards?
Yeah, and that's a good question too. I don't think it impacts the size of the individual generator set so much, but what it will likely do, it will it will drive more data centers to go to a paralleling topology. So the more common data center design today, or most common, is kind of a modular or a radial system for the backup power system, where you will have an individual generator set backing up an individual server room and maybe some of the cooling that's associated with it. And that's in that 2.8 to 3.2 megawatt range. That's kind of the sweet spot, and and that aligns well with 5,000 amp low voltage distribution gear. But that's been the preferred topology for a long time. You have your data hall genset, and they don't parallel, and they're all at low voltage. As you go towards more demand response, where you're taking the entire data center offline or potentially even uh, exporting to the grid, uh, there are a lot of advantages to a paralleling system. So having all these generators paralleled at medium voltage for that um, for a system like that. Um, it has advantages if you are doing demand response. If you're taking the whole system offline, it can result in some fuel savings. For example, many of these uh, the generators that we typically see there, they're not usually going to be fully loaded, or some of them will be close to their maximum, some of them will be half loaded. So you wind up with a lot of stranded capacity in that type of design. So with a paralleling system, if you're aggregating the sources and the loads, you could wind up with less stranded capacity because you can shut off engines that you don't need. So whereas with a modular design, if you have 60, the total load is only 60% of the capacity, you still have to run all of the generator sets. Even if certain generator sets are only at 30%. Whereas in a paralleling design where you're aggregating the sources and the loads, you can shut down the generators you don't need. So if you only have 60% of the load, you only really need 60%. I mean, you're going to want some headroom, but you can shut off some of the generator sets, and you're saving fuel that way. And when you're running, if you're doing this flexibility and you're running 500 hours a year instead of 50 hours a year, that fuel savings um, can become significant. I know, and some hyperscalers looking at a paralleling system, kind of taking that a step further, um, you you could potentially size your on-site power system closer to average rather than peak load, and eliminate some of that stranded capacity. So if you have, um, you're always going to have some redundancy. So you might have your total generator capacity being 110% of the maximum load, but if the average load is only about 70% of that capacity, maybe you can size your paralleling system a little bit less, save some capex there. Um, Not every data center operator can do that, particularly colos, which will have service level agreements with their customers. But some can size their on-site power closer to their um, to their actual load. I had mentioned natural gas a little bit earlier. One thing that I didn't mention about natural gas is uh, generally for the same physical footprint, you don't get as much power out of a natural gas engine as you do a diesel engine. So if the sweet spot in a data center design is say 3 megawatts, the population of manufacturers that make 3 megawatt gas generator sets is much smaller than than operators that make diesel generator sets. So an advantage of a paralleling system is the size of the individual generator set doesn't matter so much. It doesn't necessarily have to be sized for a certain server room. It's just if you have a 30 megawatt plane, any combination of generators that equals 30 megawatts will work. So it allows you to use a smaller generator set if that's all you have, or in some cases if you're some of the kind of medium speed operators might make 5 megawatt or even larger natural gas generator sets. And having this paralleling architecture allows you to do that because you're decoupling the size of the generator set with the power requirement of the server hall. The other advantage to a paralleling system, as we think about AI and the power density of AI that I'd mentioned earlier, um, with with that very large amount of power in a very small space, it can kind of shrink the physical size of your server room. Um, However, with low voltage distribution, that you won't be able to shrink that size. If you still need 5,000 amps, you still have that 5,000 amps worth of distribution. However, if you decouple that and you do your distribution at medium voltage, you can shrink that footprint as well. So having this more medium voltage distribution um, uh, is advantageous there. Um, and when we talk more medium voltage distribution, again, that would likely imply more medium voltage generator sets. So a medium voltage paralleling architecture uh, would support that type of power density. The other comment about, or the other thought about AI, native to the servers, that it's all DC. And so if we're kind of reimagining the electrical distribution system in a server room, there's advantages of doing some of this distribution at more of a high voltage DC. You have less losses, and you're connected more directly to the server room. And what we're likely to see in support of that will be some of these solid state transformers that can take a medium voltage AC and transform it directly to 800 volts DC. And so kind of getting back to the question, what does the AI and grid interactive operation have to do with generator sizing? Again, not so much generator sizing, but I think it does reveal some advantages in doing a medium voltage paralleling architecture.
All right, yeah. So savings and flexibility are definitely top of mind, but it sounds like sustainability is also front and center. Um, how should engineers be thinking about life cycle emissions or like even fuel flexibility? You talked about this a little bit, or future proofing backup solutions to support the ESG goals.
Yeah. So that's a good question. That sustainability and life cycle emissions, that's becoming a big thing in the data center space, and it's a big thing for Cummins as well. So we have a corporate group that looks at sustainability, and we will do what's known as LCA's life cycle assessments for our data centers, and that's becoming. I would say the hyperscalers are really driving that requirement, but that is becoming an ask of all their key suppliers, and that life cycle emissions, that goes not just to that isn't just tailpipe emissions. That's all of the carbon associated with the manufacture of the generator set, going down to the level of the steel. How green is the steel that you use? And data centers, they're not just asking their generator manufacturers, they're asking their steel suppliers, and all of their concrete suppliers to produce these life cycle assessments. And so that's something that Cummins supports, and all our colleagues in the generator set industry are supporting. So that is something, if a consulting engineer, a data center operator maybe asking you to use that as a criteria in your selection of suppliers, or they may be going directly on the suppliers with that as well. So that's part of the life cycle carbon. HVO is another another trend that we're seeing in that area. For those who might not be familiar, HVO is hydrotreated vegetable oil. It is literally a drop-in replacement for diesel. You can run your diesel engine on HVO with no modification. There might be only a very slight um, uh, reduction in maximum power, but otherwise it's literally a drop-in replacement, and it's about a 70% reduction in carbon intensity compared with traditional ultra low sulfur diesel. So that's something that we see data centers wanting to use to help meet uh, their own carbon goals, and it actually is in terms of carbon, it's lower carbon intensity than natural gas, and it's actually lower carbon intensity than most hydrogen that you can buy today. And where we get at that is in the carbon associated with producing the hydrogen. So most hydrogen that you can buy today is extracted from natural gas. So in terms of carbon emissions, the emissions are on the same level as natural gas. So HVO has a lot of promise there. Um, The challenge with HVO is the supply chain, and what we see a lot of uh, the hyperscalers or the large colos, they'll always commit to first fill with HVO, and they'll always try to get it, but after you've run, um, they're not always able to commit that they'll replace it with more HVO. They may just have to replace it with diesel, which is actually an advantage of HVO because you can mix the two fuels. So we see that that has, I mean, it's almost future proofing for free because you don't have to do anything to your design to get it. I shouldn't say free because it's more expensive than diesel and harder to get. But I think that's something that we see great promise in, particularly if the supply chain is able to mature in the coming years. Since I mentioned that, though, one thing I should say about HVO is it's a substantial reduction in carbon, but doesn't reduce NOx, not to any appreciable amount. And so it doesn't help with your tailpipe emissions or your air permitting challenges. So it doesn't help that way, but it helps meet the sustainability goals. The other thing I would talk about when you think about future proofing, um, one thing I would say, rather than talk about different fuels and future proofing for hydrogen at some point in the future, which is a good possibility that I mean it has challenges, but there's good potential in hydrogen being available in more substantially in green hydrogens, particularly in the future. But I would say something to think about for in terms of future proofing would be battery energy storage. And the reason I say that is it's really an enabler for renewables. It's an energy source itself, but the challenge with renewables is, if photovoltaic and wind is they're intermittent, right? They don't deliver power 24/7. You need the wind and you need the sun to get them. But energy storage is a way of future proofing your site. So even if you have a site that you know doesn't have wind or PV available to it immediately, if you're using batteries to do this flexibility demand response, and you already have that on the site, um, if at some point in the future in your region there is, say, an offsite wind farm or solar farm available, you've already got that energy storage on site, so you could it makes the transition from a conventional power plant to this renewable power plant much more seamless. You're able to accommodate that. So when I think about future proofing, I think having on-site battery energy storage is one of the best things and most tangible things that you can do.
Okay. Well, let's keep on that train of thought. Looking at the future, how is Cummins investing in next generation technologies, whether it's fuel cells or microgrids or even digital tools? I mean, we need to meet these needs of high performance sustainable data centers. What is Cummins doing?
Yeah, well, that's a great lead in, so that I can talk about our. We are actively investing in battery energy storage systems. Um, we've released our first line of batteries for the 50 hertz market so far, aimed at more commercial industrial, and that's a few nodes up to 1 megawatt, 2 megawatt hours, and we are. Not only looking at expanding into 60 hertz markets, but we actually are going to begin manufacturing batteries in the United States in over the next couple of years. Like right now, um, our battery modules are coming from Asia, as most people are, but we do have partnerships to start building those in the United States, and that's not just for power generation. That's for our mobility markets as well. Um, we also are investing in hydrogen technologies, um, both PEM fuel cells, the hydrogen powered uh, 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 proton hydrogen powered fuel cells, as well as electrolyzers. So electrolyzers are the equipment that um, is able to uh, produce hydrogen. Basically, just electricity in, and you're able to produce hydrogen on site. And that hydrogen is something that's going to be as clean as your power source. So we talk about having green hydrogen. And what that means is you are extracting hydrogen from water using power from a clean energy source. Would be green. Our electrolyzers can produce hydrogen from any power source, but it's only considered green hydrogen if it's coming from a clean power source. So that's an important part of our business as well. Um, uh, you mentioned microgrids. And we see microgrids, that is something that's important to us, and we are ramping up our capabilities. We see microgrids. It's really um, it's really a company capability rather than a product, right? Because the microgrid is something it takes power from any number of sources and basically optimizes their operation. So you're optimizing. Are you optimizing revenue for doing a demand response program, or are you trying to minimize your carbon? And are you also trying to make sure that you have redundancy so you can hit your 5 nines reliability targets. So we are investing in our microgrid capability. So our ability to, we see ourselves in the near term as providers of diesel and natural gas generator sets, and also batteries and fuel cells in the future. Um, Maybe not, not providers of solar panels or wind turbines, but we see the microgrid controls, the system controls that ties it all together, and also the expertise to define and implement a system and support our customers with all the appropriate permitting. So that, I mean, the microgrid, it really is, as we see that's a business, not so much a product or a technology. And we are very actively developing our capabilities there as well.
Okay, Rich, it's finally advice time.
Uh-oh.
What's your advice to consulting engineers, operators, or even developers working on power infrastructure in this fast changing landscape? What would you say? How should they engage with Cummins to deliver smarter, faster, greener solutions?
I think what I would say is look at us as your partners, not just a provider of equipment. That's kind of what I was on about a little earlier with the microgrids. So um, we want to be partners, and maybe a diesel generator set isn't the right solution for a site. Maybe it's a natural gas and best combination. Maybe there is a hydrogen source where a fuel cell will make sense. But I would say you want to take an all of the above approach with your with your power requirements. Um, so look at it with an open mind, and also um, you want to make sure you're engaging with local authorities. Both uh, you know every every air quality board has slightly different regulations, so you want to make sure you're working with someone who has uh, who has the contacts with the air quality boards, has um, has relationships with various emissions consultants. Um, Also, every utility operator is going to have some slightly different requirements. So you want to look at supply, not just equipment suppliers. Look at them as partners, not specifically just equipment suppliers. So uh, that would be my response. So as we think of the changing power grid, we're going to need lots of different sources, and every location is going to have some nuances, and I would say you're going to need to have partners that have experience working in all kinds of different markets with different types of technologies.
Awesome. Well, thanks for your time today.
All right, thank you.
Yeah. I've been chatting with Rich Scroggins from Cummins. I appreciate your time as we discuss this topic. If you'd like more on data centers and power requirements, please visit Consulting Specifying Engineer at www.cscmag.com. Thanks so much and see you next time.